Welcome back everyone to part 2 of blurring and smoothing. In part 1 we actually didn't really code anything, we just explained a little bit about blurring and smoothing, what gamma correction is, and also what a kernel is. Now it's time to actually use these functions of OpenCV. Let's get started by opening up a Jupyter Notebook. Alright, we're going to start off with a couple of imports. I'm going to import CV2, and then just in case I need them later on, we'll import NumPy as NP, and we'll be displaying images as well. So we'll say import matplotlib.pyplot as PLT and matplotlib inline. Okay, now the image we're going to be using is an image of bricks, and the reason we chose this image for blurring and smoothing is because usually you can see each outline of each brick really clearly. So what we're going to be doing is blurring this image, and later on we'll actually also add some text to the image to see different effects. However, what I want to do is do a couple of convenience functions. And in fact, I'm actually just going to copy these functions directly from the notebook. So go ahead and feel free to do the same. This first convenience function that's in the notebook for this lecture, it just loads the image. Because we're going to be blurring the image and the blurring happens in place, I want to have a quick function that allows me to just quickly reload this image over and over again. However, you may need to actually edit the string here. So I'm going to edit it because my data folder is in the same directory as this notebook. So I'm just going to get rid of that // Okay, so there's my load image function. Let's check that it works. We're going to say load image, and there it's loading the array of the image. Okay, so that's working. Then I'm going to copy and paste the display image function. So let me copy that. And again, I'm just copying this from the notes, and we've already seen this function a couple of times. It just displays the image a little larger. And now with these two functions, I should be able to do the following. I is equal to load image, and then display image on I. And if you run that, you should see the bricks right here. Again, it's just a white wall of bricks with some blue painted on top of it. And we're going to be performing different sort of blurring and smoothing effects. The very first effect we're actually going to be performing though is gamma correction. Recall from the previous lecture that gamma correction allows you to increase or decrease what is perceived as brightness in the actual image. And it's pretty straightforward. All we need to do is load up the image, which we already did, and then choose a gamma value. If you choose a gamma value of less than 1, then what you're going to end up doing is making the image appear brighter. So we'll choose 1/4 as our gamma, since it's less than 1. And if you want to affect the image, all you need to do is say np power, and then pass in the image, and then pass in the gamma. So all this is going to do is take every pixel value in the image and raise it to the power of gamma, which in this case is 1/4. And let's have this be the result. And then we're going to display image of result. So whoops, make sure we have that image not defined. It's actually just I. There we go. Run that. And now we can see because we chose a gamma of less than 1, the image appears to be brighter. And as you start going with smaller and smaller values of gamma, like 1/10, and you run this again, you're eventually just going to fade out into white. So keep that in mind. If we start choosing gamma values that are above 1, you'll end up making the image appear darker. So if I choose a gamma of 2 and rerun these, then notice what happens. Now my image appears darker. Here's my original image, and now look at the blue here. It's much darker. And you can choose really high values of gamma, like 8, and you'll see that it almost starts looking black. Okay, so that's gamma correction. Again, the practical effect is just increasing or decreasing brightness of the image. And all you really need to do for that is just a little bit of simple math. Take the pixel array values and then raise them by the power of gamma, which is conveniently done with np.power. So this does that for all the layers across the image. Now we're going to move on to our first blurring. And the blurring we're going to do is what's known as a low-pass filter with a 2D convolution. And to start off, the first thing I want to do is I actually want to write some text onto this image. And the reason for that is sometimes it's a little hard to see the difference between a couple of the blurring and smoothing techniques. And if you write a little bit of text on the image, that differentiation becomes a little more clear. So let's start off by just loading our image fresh. We will say img is equal to load image or load img. And what I'm going to do is say font is equal to CV2 font, and I'm going to choose Hershey Complex. I just did tab autocomplete there. And then CV2, we're going to put some text onto that image. So we'll say image. The text we're going to write is bricks, and the actual position we're going to put it in is at 10,600. The font face we're choosing is the font that we just defined. The font scale is going to be a little larger, around 10. And the color, just to make it obvious against the blue, I'm going to make it red, so 25500. And then the thickness is going to be 4. Okay, so let's actually display that image. And don't worry if you get this sort of value here. Basically what that means is you have some values that fall outside of the range 0 to 1 or 0 to 255, so it's just clipping them down. Again, if you get this warning, not a big deal, you don't need to worry about it. Okay, so here we have now the image of the bricks, and now it says bricks on top of it. We're going to be constantly reloading this image, so you're going to see me come back and copy and paste this code a bunch of times. So keep this code handy. It's going to be used over and over again in this lecture. But the reason I added this text is I can see, due to this particular font, that there is some lines in between some of the markings of the letters. For example, in this I, there's some space in between those two lines, or this R, there's some space in between those lines, same as in that C and that curve and that B. When we actually perform blurring and smoothing, those spaces are going to be blurred out or smoothed to different degrees depending on what kind of smoothing techniques we apply. So that's the first thing we're going to do. And the next thing we're going to do is set up our kernel for that low pass filter. And the kernel for this is a really simple one. The kernel we're going to decide on is NP1s. The shape we're going to give it is 5 by 5. Remember from the previous lecture we saw a kernel of 3 by 3, so this is just a little bit of a larger kernel. And the data type we're going to choose to make sure everything is compatible is, say, NP float 32-bit. And then I'm going to take that whole thing and divide it by 25 so that everything is 1 over 25. So if I check out my kernel, notice it's a bunch of 0.04. And if you did 1 over 25, whoops, not 1 over 15, 1 over 25, that's equal to 0.04. So here we have a bunch of 1s, and all those 1s I divide by 25. So now I have a bunch of 0.04s, and that is my kernel. Then what I'm going to do is just apply a 2D filter on it. The syntax for that 2D filter is simply going to be CV2 filter and then 2 capital D. And the output of this is going to be any variable you want. Often people just say DST as in destination. So we have that destination output, that DST variable, and that's going to spit out after you apply the kernel to the entire image. So we have CV2.filter 2D, and then what we're going to do is pass in the image that we want to actually apply the filter to. And the second parameter is known as desired depth. And what you do is you just pass in -1. That way the output depth that you desire, -1 means I want the input depth to actually assign the desired output depth. And if you're a little curious what desired depth actually means, you can check out the links in the resource for this lecture. There's some good Stack Overflow links, as well as links to the documentation that describe desired depth in a little more detail on image filtering, as well as image type versus image depth. Really, for our use case, we don't really need to worry about that. We're always just going to be using -1, which defines that we want the output depth to be the same as the input depth. And again, there's more explanations here. Okay, so we're going to come back out here, and once we've chosen -1 so that the input depth is the same as the output depth, what we want to do is pass in the kernel. Remember, we already defined the kernel up here. So we have this variable, we're going to apply the entire kernel to it, and then once we do that, let's display the resulting image. We'll say display img, and then DST. We run that. Again, you don't need to worry about this particular warning. It's just telling you that it clipped some values that were either above 1 or above 255. And you'll notice that things do appear to be blurred now. If we take a look at the original image, notice here that we can see the bricks very clearly, and we can see the blue in between these lines in the text. And that's why we have the text there, because it makes the blurring and smoothing really obvious. And if we come back down here, you'll now notice that there appears to be almost like a pink in between where there used to be that spacing in the letters. And it doesn't happen to every single letter, but it definitely happens to the majority of them. And I would encourage you to play around with the kernel size, make it smaller, make it larger, choose different values, and see how that affects the actual image. Okay, now let's go ahead and reset everything. What we're going to do is come back up here and then copy this command. So this is a command we're going to be copying all day, so you can even feel free to functionalize it. I'm going to copy it, come back down here, and reset my image. And then I'm just going to print something like reset, that way I don't see that giant array. Okay, so we've reset the image, we have that loaded image, and now we have that fresh text on it. What we're going to also show you now is how you can smooth based off averaging. And as you may have expected, there's actually a default blur kernel that we showed you in the previous lecture. You can actually just apply that kernel by saying cv2.blur. And then you pass in the image, and then you pass in whatever kernel size you want for the default blurring kernel. So previously, we manually defined the kernel and then used that filter 2D to apply the kernel to the image. Now we're just going to use CV2's built-in blur kernel. Same concept here, except now they've chosen specific values for the blur. And then we're going to say blurred is equal to that, the result of blurring the image, and let's display those results. So display image blurred, we run that, and then we can see again here that the image has clearly been blurred. The lines are not so distinct, and then we can see a little bit of that pink coming along in the bricks. And here, I would again encourage you to kind of play around with the kernel size. So we can even make this something like 10 by 10 and see how that affects the actual results. So you can run that, and you can see as the kernel got really large, then the blurring became more intense. Okay, so there's other things like Gaussian blurring and median blurring, which just take a group of pixels and then go along and calculate the averages and then make those the outputs. So, as you may have suspected, we're just going to copy and paste this line of code. We're going to reload the image fresh. So now I have my fresh image, and you can always check on this by just displaying it. So if I say display image, I see that nice crisp outline with the bricks. So I'm going to comment that out. And then let's apply Gaussian and median blurring, which is essentially just averaging techniques. Very similar to what actually the cv2.blur does. But in this case, all we need to do is say cv2.Gaussian blur. And what this does, as far as arguments it takes in the source image, the kernel size, and then what you choose as your sigma value. And for your sigma value, if you come down here, the sigma is going to be the standard deviation. And usually people just tend to assign sigma x, and then sigma y is then set automatically to sigma x. Okay, so what we're going to do here is pass in the image, pass in our kernel size, again, things you can play around with, and then just by playing around, I decided to choose a sigma value of 10. So we're going to say blurred image, and let's display that blurred image. And also something I want you to keep in mind is there's no right or wrong way to display images. There's no right or wrong kernel size. A lot of it is often just guess and check, see what works well. Specifically, see what works well with the pipeline of application you're trying to discover. So if you're trying to do edge detection, you'll probably try out a bunch of different blurs and then see which one works the best with your particular edge detection technique. But let me go ahead and run this. And here we go again. We can see the blur happening. So you can see a little pink here. The lines are not so clear. And what we're going to do is show you a very similar blurring technique. So we went with Gaussian blur. We showed you blur. We showed you our own custom kernel blur. And another one that you can do is median blur. For the median blur, all you need to do is say cv2, median blur, and then the parameter is just going to pass in is the image, and then k size, so the kernel size. This has to be a square kernel, so it ends up just taking one argument. So we can just say 5, which basically translates to 5 by 5. And what we do here is just say median result, or really whatever you want to call that variable, and let's display the results. So we'll say display image, and say median result, run that, and there we have that sort of blurring. So this one is really interesting because you'll notice that the foreground here of this text, it doesn't actually appear to be as blurred in the middle of these lines as before. So if we come back up here, we definitely see that pink hue coming into play, as well as the background being blurred. With this sort of median blurring, it actually tends to be really good at removing noise from an image while trying to keep certain details in check. So you'll notice that we've removed what essentially is some sort of noise from the bricks. It doesn't look as detailed, but we're able to keep in the detail of the actual text of bricks. So that's what makes median blurring a really interesting technique for reducing image noise. And if you've ever played around with Photoshop and you've seen some filters for removing noise from an image, usually what they're doing is they're actually just applying a median blur. So let's go ahead and see this in action in a more realistic example. Right now we've been playing with this bricks image, which isn't a really realistic use case. Instead, I want to show you an image that already has noise and how we could remove noise from it. We're going to say image, or img, is equal to cv2, imread, and I'm going to read in from the data folder. There is a picture called sammy.jpg. And then we need to actually correct the color for this image. We will say CV2, CVT color, pass in the image, and as usual, we'll say CV2 color blue, green, red to red, green, blue. So run those commands and then display this image. And you should see a picture of my dog, Sammy. Okay, so this is a picture of Sammy. This is what a normal picture of him looks like. And what I ended up doing was I decided to make a noisy version of this image. So I went ahead and with a little bit of code, I made a noisy image, and I want to load it for you now. We're going to say noise image is equal to CV2 image read, and in that same data folder, there is a picture called Sammy noise. And this one I actually already color corrected for you. So if you run this and display the image here, if you say display image, the noise image, you'll notice it's actually the same image, but it's way noisier. So I added a bunch of noise to this. You can see here, the way I did this is I just randomly chose values or randomly chose pixels and made them random values. So that's why there's kind of this weird noise that's happening here. So here's the original image, and then here's the noisy version of the image. Now let's see if we can use median blur to try to fix this sort of noise, try to remove it. So what I will do is say median is equal to CV2. I'm going to call the median blur function. I'm going to pass it on the noise image, and then pass a 5x5 kernel for the median blur. And 5 actually ends up being a really common value. So I would recommend starting with 5 and then working your way higher if you need more blur. Then let's display the result of that. We'll display median. So running this, we get to see that it looks like the noise has been reduced. Now it does come at the cost of some detail. If we compare this to the original image, we can see kind of the finer details of the grass. And this is actually a really large image. It's more than 1200 by 1000, more or less. So we do have quite a bit of detail here. This is the noisy image, and if we did a blurring on that, we got rid of a lot of the noise. What ends up happening is it blurs in with the pixels that surround it, and it comes at the cost of a little bit of detail. So you can no longer see that fine detail of the grass or maybe the trees in the background, but essentially, from a human's perspective, it looks a lot better than what we had before in this noisy image, because here we just have a bunch of random pixel colors. Now we're able to reduce that noise. Okay, so that's it for the median blur. The last thing I want to show you is a bilateral filtering. It's just another way to blur an image. So just for the sake of completeness, I want to show it. Let me reload in this image right here. So I'm going to copy and paste this load image with the bricks, scroll all the way down, run that. So we have our bricks reset. Let's make sure of that. We'll say display image, and there's our bricks. And then if you want to perform a bilateral filter, we actually won't see this later on in the course, but I do want to show it just in case you're interested in it. All you need to do is say whatever the output is, go with CV2 bilateral filter, and then the parameters here are source and then D, sigma color, and sigma space. And you can actually check out this link. It explains how bilateral filtering works. Essentially what it attempts to do is reduce unwanted noise and keep edges fairly sharp. However, it's usually slower compared to other filters. So we're just going to use some default values here. We'll say image 9 and then 75 and 75 for those sigma values. And let's display that image. So we'll display the blur. And you notice now it looks blurred, and it's actually been able to keep a little more detail around the lines in between the letters of the bricks. So it's kind of similar to median blur as far as being able to reduce noise in an image and still keep edges really well. Okay, so that's it for this lecture. Again, just a bunch of different blurring techniques. Usually we're just going to go with the simpler ones like a median blur or just the built-in blur. The main idea here is that we can reduce noise in images that are noisy, or we can reduce the amount of detail we need when we're performing other tasks like edge detection. As long as you feel comfortable with the idea of applying a kernel to an image with Filter2D and with just applying any sort of general blur, then you're pretty much good to go. All right, thanks everyone, and we'll see you at the next lecture.